Bismillahirrahmanirrahim. Welcome to the Electrical Engineering YouTube channel. In today's lecture, I am going to discuss about various tests which can be performed on induction motors. The purpose of performing these tests on induction motors is to first to find the motor parameters, and the second purpose is to find the losses which are taking place across the motors. So the first test is called no load test, and in this test there is no mechanical load connected at the shaft of the induction motor. And we know that whenever there is no load or the motor is running freely, then in that case the rotor speed will be maximum. And when the rotor speed is maximum, the slip will be minimum. Or we can say that the rotor is almost running at the speed of the rotating magnetic field, or Nr is approximately equal to Ns. So this is the preliminary equivalent circuit of the induction motor per phase equivalent circuit. Here we have stator and the rotor parameters, and these are the magnetizing parameters. This is R2 and this is R converted. So the transformed equivalent circuit of the induction motor under no load condition can be drawn like this. And in this case, these are the stator parameters. This R naught is very high, so we can safely ignore this component, and this is JXM. And at this point, we know that S is approximately equal to 0, and in that case, this R2 into 1 minus S over S, this term will be very high. Or if we add this R2 and this R converted, we will get R2 over S, and that R2 over S will be very high, or we can say that R2 over S is almost equal to infinity, which means that this equivalent resistance at the rotor side can be replaced by an open circuit. So in this case, this friction and windage loss resistor is very greater than this magnetizing reactance, and similarly, this R converted is also very greater than this R2. Okay, so this is R2 and this is the magnetizing reactance. So this component or this branch can be ignored, and we can assume that all the current which is entering the stator winding of the induction motor will be passing through this magnetization inductance branch. So in that case, we can calculate the core losses, or we can say that we can calculate all these three losses, which are collectively termed as the rotational losses, and we can calculate the losses taking place across the stator winding. So the stator copper loss is equal to 3I1 square R1, and the total input power is equal to this stator copper loss, and this the sum of these three losses, and these three losses are called rotational losses. So we have to apply, or we have to connect a power meter over here. So we have to also put a mechanism to calculate or to measure the voltage applied and the current flowing through the stator branch. So this is the stator copper loss, and this total input power will be equal to this. So this watt meter which is connected at this input side will be giving the total input power, and from we can also calculate measure the current which is entering in the stator of the induction motor, that will be given by I1. So first we have to calculate this R1. So this R1 is the stator resistance. So I will discuss the second test in which I will show you how to calculate this stator resistance of the induction motor. So when we have this stator resistance, and we can easily measure this I1 by putting an ampere meter over here, we can calculate the stator copper loss independently. So this total input power which is consumed by the motor will be given by a watt meter which is connected over here. And we have also calculated this stator copper loss. And when we subtract this input power from the stator copper loss, we will get the collective rotational losses. So this no load test is helpful for calculating the stator copper loss and these rotational losses. And we can also calculate the equivalent impedance of the induction motor under no load condition, which is equal to the ratio of V phase divided by the stator current, and that ratio will be given by the sum of the leakage reactance across the stator and the magnetizing reactance. So the sum of these two reactances will also be calculated by this no load test. So we will move on to performing the other tests which will provide us other remaining parameters associated with the induction motor. So the second test is very simple, and that test is called DC test for stator resistance. And for performing this test, we must have such an arrangement. So these are the three-phase stator windings, and we have to apply a DC voltage across these two any two terminals of this stator winding. So whenever we apply a DC voltage across the stator, the inductor becomes a short circuit. So only the resistance of the winding will be appearing in this equivalent circuit, and this resistance is actually the resistance of the copper windings, and this the resistances are very small. So we must have a current limiting resistor connected in series, and there is an ampere meter which is connected in series, and we have to measure this VDC or this DC voltage at this terminal, not at this terminal but at this terminal, because these are the voltages which are applied across the stator winding phases. So this is I1 and this is actually our VDC, and by applying Ohm's law we can calculate 2R1 by dividing VDC by this IDC, or by dividing this with I1. And we have to make sure that this I1 shouldn't exceed the rated current, because since we are applying this DC supply, this resistance is very very small. So if we increase in an uncontrolled manner this voltage, this current can exceed the rated current, and in that case that winding can damage. So this voltage should be increased slowly until we reach the rated current, and at that instant we will measure this voltage and this current, and their ratio will give us 2R. So when we divide this ratio by 2, we will get R1. So this test will provide us the stator winding resistance, and this stator winding resistance will be used in this test to calculate the stator copper losses. So the third test is called locked or blocked rotor test, and in this test the rotor is actually locked such that we will apply a small voltage across the stator winding, and the rotor shouldn't move. So we have to put some mechanism so that the rotor cannot move, even if some force or some power will be applied across the rotor, but still we must forcefully lock the rotor such that it cannot rotate. So in this case, the slip will be equal to 1, because nr is equal to 0, and this r2 over s will be equal to r2. And we know that this r2 is the rotor winding resistance, and its value is very very small, and therefore we must keep this voltage very very small, and we should very very slowly increase this voltage such that the motor is drawing the current which is smaller than or equal to the rated current. If we increase this voltage in an uncontrolled manner, since the resistance appearing in this equivalent circuit is very small, the current can exceed the rated current, and in that case the whole motor windings, stator, both the stator and the rotor windings, they they can damage. So this test should be performed in a very controlled manner, and this there should be an ampere meter in series with the stator winding, which is giving the current which is drawn by the motor, and that current should be smaller than the rated current. So this is the transformed equivalent circuit of the induction motor, and in that case these magnetizing parameters are very very greater than these rotor parameters, which can be seen over here. So xm is very very greater than r2 plus jx2, and rc is very very greater than r2 plus jx2. So we have to neglect these two parameters, and in this case all the current which is flowing through the stator will enter the rotor windings, and we can calculate the power factor of the motor. So this is the expression for a three-phase power, and power factor is given by cos theta. This input power is first measured by applying a wattmeter at these stator terminals, and we will also have a mechanism to measure the voltage and the current drawn by the motor. So all these parameters P, Vt, and IL are known, and power factor cos theta can be calculated by this expression. Similarly, we will calculate the locked rotor impedance, and its magnitude is given by the ratio of V phi divided by I1. And V phi is the phase voltage, and Vt is actually the terminal or line voltage. So that line voltage can be converted to phase voltage by dividing it by square root 3, and this is the line current. So in star connection, the phase current and line current are same. So this I1 is equal to IL. So locked rotor impedance is equal to the real part plus the imaginary part. And this the real part is actually the horizontal component of this locked rotor impedance. This imaginary part is actually the uh, vertical component of this log rotor impedance. So this is given by J ZLR magnitude sine theta, and R log rotor is equal to R1 plus R2, and this is the log rotor resistance, which is the sum of the stator and the rotor winding resistances. Similarly, log rotor reactance will be equal to X1 plus X2. So here we will have another useful discussion. This log rotor resistance is constant at any operating frequency, but these reactances are different. If we are performing the test at different frequencies, different values of these reactances will be given. Okay, so at the test frequency, these values are represented by the prime variables. And first of all, we will calculate the rotor winding resistance, which is given by RLR minus R1. This R1 is given by the TC test for the stator resistance. And this is the sum of the leakage reactance across the stator and the rotor windings at the test frequency. And for the rated frequency, for example, our rated frequency is 60 hertz, and we are performing our test as 30 hertz or 35 hertz. These parameters will be different. So first, for example, we have calculated these parameters at 30 hertz. Then these will be the parameters at the test frequency represented by the prime variables. But at the rated frequency, these free parameters can be calculated by applying by dividing f rated with the test frequency and this XLR prime. And this will also give the sum of the leakage reactance across the stator and the rotor windings. So these are the three tests which we have discussed in this lecture, and these tests are very important to calculate the losses. So these losses across the induction motor will give the efficiency, and these tests also provide the parameters in the equivalent circuit of the induction motor. So I hope you have understood the concepts which are explained in this lecture. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.